Here is a series of amines, and we're going to be analyzing to determine which of these is the least soluble in water. And again, we'll be talking about intermolecular forces. What is that we have in this molecules, and what is that is in the liquid. And again, I'm going to be drawing what is my water, so that we remember the interactions between water molecules. And the strongest being hydrogen bonding. And here is some of those. So, okay. And now for this solution to be favorable, we need to be replacing these interactions with new interactions of the same type, so that the enthalpy term is favorable when I do for my dissolution. So now let's talk about the type of amines that we have here. All of these are amines. Think about this being derivatives of ammonia. When I replace one of the H's here by an R group, I'm going to say NRH2. Oh, well, let me choose. I'm going to rewrite it like R and H2. So I have replaced one of the H's, so this is a primary amine, one R group. If I replace two of the H's here in ammonia by R groups, let's say that I have the same, okay, we'll have another. So let's do two R groups and only one H. This is a secondary amine. And if I replace the three H's by R groups, then I have a tertiary amine. So, and this is what's going on here. This at the nitrogen, let's put the lone pair everywhere of the nitrogen. Here you have two R groups, so that is a secondary amine. Here you have 1, 2, and 3, so it's a tertiary amine. And this you have one R group. This is this case, so that is a primary amine. Now let's look at the interactions. Notice that I have, well, here I have 5 carbon atoms, so 4 here and 1 more, so 5 carbon atoms, 1 nitrogen. So in regards to the molar mass, it will be the same. This is why this series allow us to compare that, because now we don't have the effect of the mass playing a role into this. Now, let's analyze the type of interaction. So here, in all the molecules, I'm going to have London dispersion forces again. We remember that these are fleeting dipoles. I'm going to write it like so, later. So check mark here, check mark, check mark. All right. So the second intermolecular force that we'll be considering is dipole-dipole. And remember that here, nitrogen in your periodic table, I'm going to draw a little bit of the periodic table here. Let's say the second period. We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and that's neon. But well, I'm going to erase neon for now. In these elements in the second period, electronegativity increases in this direction. Electronegativity increase. So the most electronegative is the fluorine. But between here, carbon and nitrogen, so nitrogen is more electronegative. So I will have a dipole here. Carbon is delta positive. Nitrogen is delta negative. And another dipole over here, delta positive. The carbon delta negative are the hydrogen. And let's redraw that H with the bond explicitly. So this would be like that. And of course you will have another dead dipole pointing to the nitrogen. But what is that we see? So whenever you have polar bonds, so you can have interactions, dipole, dipole. So let's give that a check mark. dipole, dipole. I have those. Here, again, you see that I have a polar bond between carbon and nitrogen. And I will have this. And another vector like that. But this molecule still have a dipole moment. This molecule is not planar. This molecule about the nitrogen, this is, even though you have 3 hydrogens, is trigonal pyramidal. So, and you will have some dipole there. So it's not a total cancellation. I'm going to draw a little bit of a drawing of ammonia. So ammonia is like that. So you place those when you do your VSEPR, all of the, think of the 4 electron domains in the corner of a tetrahedron. And now for the shape, we're not seeing the lone pair. So you see these 3, but they're not on a plane. It is a trigonal pyramidal. It's just something like this, with 3 legs, let's say, and the lone pair here. Okay, so you will still have some dipole, even though pointing towards the nitrogen, because it's not planar. So you will have some dipole, but definitely not as large. So we're going to say, yeah, dipole. And of course, we will have that interaction here, because again, nitrogen is more electronegative than carbon. So I'm going to draw that vector. But now I'm going to replace something here. Let's change this marker is better. Yes. And now I'm going to redraw these 2 hydrogens to make them more explicit. So I'm going to do H and H. That was set as a primary amine. Of course, we're going to have dipole. So, yeah. Let's analyze the last force, which is what we have here, hydrogen bonding. So, here I do have a hydrogen attached to nitrogen, and either this or with oxygen, such as in water, we will have hydrogen bonding. So I have hydrogen bonding here, and I'm going to erase all that, not to be confused. I need to be writing a little bit more. So I'm going to write now my hydrogen bonding. So there is a chance of hydrogen bonding because I do have this. So I have a hydrogen attached to a nitrogen. So I'm going to do hydrogen bonding. I'm going to get a check mark. But now in this molecule, you have here H's, but they are attached to carbon. Same here and same here. So no hydrogen bonding. So I'm going to cross that. I had a check mark here in dipole, but not on hydrogen bonding. In my last molecule, I have 2 H's attached to a nitrogen. So I have even more chances of forming hydrogen bond here in this molecule than I do here. So more hydrogen bonding, let's say. The question said, which of these is the least soluble in water? So the one that will not be able to replace these interactions in the water with new interactions of about the same type. And this molecule is this, because no chances of hydrogen bonding. I cannot replace these interactions in the solvent with new interactions, solute solvents. So this is the least soluble in water. So this is my answer. And of these 2, it's likely to be more soluble, having more chances of hydrogen bonding.